Okay, so we're now at the test lab for ChargePoint, and I'm here with Amir, and he's going to give us a little tour. But first, he's going to give us a little background on their design for reliability and life cycle. So, Amir, you want to give us a little background on yourself?
Sure thing, Sandy. Welcome to our advanced test facility. For reliability of the product, me and my team have to really get involved early on in the process. And that means engaging in the architecture phase where even the concept of the product is being figured out, so we can apply best practices of reliability, take learnings from predecessor products and currently shipping products, and apply those towards designing for reliability. And that means guiding material selection, guiding PCBA design, operating conditions for the design engineers that suggest we will build margin into the product's reliability. Then we move on to the prototype phase. In the prototype phase, we're getting deeper into risk analysis. Key practice that we follow is failure mode and effects analysis. And that's where we take cross-functional input and we apply that towards risk ratings for the product for a variety of different failure modes and root causes that we think might be possible. And that sets the roadmap for what we then go to evaluate through simulation, testing, and other analyses. At this phase, we also want to set clear reliability requirements where we say, hey, the product should have this target lifetime, these failure rates should be the limits of what we see in the field, and gauge the product's requirements around what the customer would expect given the field exposures and environments that the product will be operating in. And cross-functioning will agree on that, and as well as doing early testing in this phase, taking a couple samples and doing destructive limit testing, boundary condition testing to see what the limits of the hardware are so that we can set test specifications that represent the field scenarios as well. So the use conditions that we expect in the field are characterized in this phase as well. So then we enter the EVT, DVT, PVT phase where we build up large quantities of product. Actually, our team is the team that gets the most samples so that we can put these samples through these use case scenarios, these accelerated tests that then represent long-term exposure. So in a span of 4 to 8 weeks, we'll simulate 10 to 14 years of life with our testing. And our testing is waterfall style testing, as they call it, where we'll sequence different stresses as they would occur in the field. Mechanical stresses, thermal stresses, water exposure, sun exposure, depending on what specific hardware risks we're trying to target, we'll combine to create the worst case scenarios for those issues. And we're putting multiple units through each specific test sequence because we want to see that our manufacturing and materials quality are consistent across the entire production population.
So let me just do one thing.
Sure.
I think this is early vehicle testing, development vehicle testing, and this must be prototype vehicle testing, and this must be mass production.
You got the mass production right. The EVT stands for engineering validation and test.
Okay.
And then design validation test and production validation test.
Okay, great.
And so in each of these phases, each cross-functional group will have their own goals and targets. And we'll repeat our reliability testing at each of these phases. And if we find an issue at EVT phase, we will stop, do failure analysis, understand the physics of the failure so that we can guide corrective actions. Then the team will apply those corrective actions and we'll want to rebuild with those actions implemented and test to validate that we've mitigated the issue.
Excellent.
And so at the end of these 3 key phases, we want to make sure that we've met all of those requirements that we set early on so that we have cross-functional agreement that the product is ready to ship into the field. Great. Once in field, we'll want to monitor the field performance. If there are any issues that occur, study them and quickly iterate. No reliability assessment suite is perfect in a development cycle, so we'll always have opportunities to get learnings back. And during mass production phase, if there's any change in supply chain, any small updates to design or manufacturing process, we'll want to reevaluate this entire list of practices to see what we'll need to repeat to ensure that the product's reliability is maintained. So if we ship a product today, we want it to be just as reliable as when we ship it 2 years down the line.
Excellent, excellent.
Yeah.
But that pretty much sums it up. Maybe we can go and have a look at some of the stuff you do out here.
Sounds good. Yeah, that gives you a good overview. And the testing that we do can be categorized in 3 major categories. We have mechanical stress, we have environmental stress, and we have operational stress. And so we'll combine these in sequences of 7 to 10 tests per test sample. Test samples could be systems, they could be subsystems, they could be PCBAs. And then we'll do checkpoints along the way where we'll fully assess and functionally check the system to make sure there aren't any issues.
Cool.
So let's head on in. So as we walk through, you'll see the variety of test samples that we'll be testing. So you'll see sub-assemblies, you'll see full dispensers and systems, you'll see component level.
Okay, so this is the module we were looking at the other facility. Only now we can see what's inside. It's pretty tightly packed, actually. Yeah.
And so, of those 3 categories, the operational stress is one of the most critical. It's what's going to be operating in the field. So behind this orange wall, we actually have an accelerated environment where the temperature is up to 50 Celsius. And we'll have systems, Express Plus systems in there, running day in, day out with automated software. And we want to exercise all the functions. So there'll be charge output, Wi-Fi connectivity, Bluetooth connectivity, and we'll be getting as many cycles as possible on each of these. And on the outside, you'll see all these loads that simulate what a car does. We'll pull that charge out.
Yeah.
So if we go around the corner here, we have this setup running for all of our products. We have CP6000 in the back. And you can clearly see the sample sizes we're putting through each specific stress.
Yeah.
So in this case, you have more functions, such as a display that we can put at max brightness for stress, LEDs that will cycle through, different colors that they emit, and we want to get cycles on all of those.
Mm-hmm. So how long is one of these units going to be cycled for? How many months or years or whatever?
So for this specific test of long-term operational stress, we'll run this for 4+ months, actually. But on average, test plants will take, excluding long-term operational stress, they'll take between 4 and 10 weeks to complete. So in 4 to 10 weeks, we'll have an assessment on how reliable the product is going to be in the field.
So accelerated testing, because no one is going to be cycling it the way it would normally see in the field.
Exactly, right, exactly.
Yeah. Do you do salt spray tests on these things?
We do salt spray testing, and we'll
we're going to
take a look at that.
Oh, very good.
Too.
All right.
So for any product that has moving parts, when you're trying to assess reliability from a mechanical standpoint, you'll have to cycle those moving parts through as many cycles as would be experienced during the field.
Lifetime, yeah.
Exactly. So in this case, connector cycling is a no-brainer. And that's engaging, specifically focusing on contact cycling. And if we don't understand, let's say, the forces at which a user will insert or extract a connector. We'll have to run a user study to better understand what that force distribution is. So we'll put 50 plus employees through, for example, a blind user study, and we'll get that distribution of forces. And what we're doing is we're testing for the 90th percentile and above case. We're not testing for the average user. We believe that if we test conservatively for the more aggressive case, then that covers everybody under the curve. So this is an obvious one. Solar radiation. Sun exposure is unavoidable and particularly stressful in harsh environments like, for example, Arizona. And so that requires us to do extensive thermal validation in environments where the ambient is taken up to that high 50 Celsius limit, under solar load with max power output. And in those case scenarios, you can have temperatures really going high and affecting actually lifetime of electrical components. So it's critical to do that testing up front and feed that into our thermal simulations to then identify high risk points that need to be managed thermally with derating, with mechanical solutions to improve cooling. So actually we've sent this exact setup over to Arizona, and we were able to match this setup within 2 degrees Celsius. So we have confidence that it's very accurate, and you can see all those wires coming off of the system are thermocouples that give that temperature feedback.
Yeah, we heard a little bit about your smart cabling. That's a pretty good idea. If you can make that feedback loop, you can gather data all day long, or actually all year long. Yeah.
And speaking of cables, we're actually in process of qualifying the North American charging standard cable, the new NACS cable.
Yeah.
And we've already made progress on reliability risk assessment and are en route for qualifying.
Great.
Which is very exciting.
Yeah, absolutely.
Okay, if we go around the corner here. And that's that salt fog chamber you mentioned.
Yeah.
So coastal regions, you're going to see salt exposure, salt-driven corrosion, and external panels, enclosure panels need to hold up against that. Yeah. We even put full systems into that test, and it really requires us to put measures in place that protect the electronics with conformal coating on boards, for example.
Yeah.
And potting of components, potting of connectors.
Connectors, yeah.
So water ingress is another obvious one that we have to include in our test suite. So we have heavy rain, storm scenarios, pressure washing, flood scenarios. We test for all those.
What about hail? That was one of the things that that's one of the things that any of the big companies that I worked at, the OEMs, hail was really that was really an obstacle. Have you done anything like that?
So for hail, you would expect, especially in more aggressive parts of the country, you expect hailstones to be on the larger side. So impact can be a concern. Right. So we'll talk about impact testing shortly. Okay. And then you have that environment of high moisture in addition to freezing and cold environments. Yeah. So we'll test those individually, those stresses. I mean, we have the heavy water exposure in the chambers. We'll have the freezing conditions. We'll have freezing condensation conditions. And then we have the impact test. So the combination of those should build us confidence for the product in a heavy hail scenario. And the key thing about water ingress testing is with all of the protection measures in place, I have high confidence that the product will pass brand new out of the box installed. But the question is, how will it fare 5 years into life, 10 years into life, when the gaskets and seals have been worn down and those enclosures may or may not hold up as well. So we have to apply aging tests and stress tests as a precondition to water ingress and make sure for reliability we keep that water ingress protection even late in life.
Very good.
Okay, so going back to mechanical stresses. And this is that impact test we talked about. So our products are rated to IK10 impact resistance, which is the highest impact resistance you can have for IEC standard. And we will target all the locations that would be high risk of failure. So component dense locations like this center module. And of course, at enclosure points as well. And the key is that we have to maintain all of our ingress protection if there's any sort of crack initiation or damage to our enclosure after an impact event. So we'll actually run this impact testing at sub-zero temperatures, -40 Celsius, also at hot temperatures, 70 Celsius. So you can imagine at the low end, you're going to have more brittleness, and at the high end, more
malleability.
flex, more malleability.
So it looks like everything here could work. Can you give us a demo on whacking it?
So the equivalent of an IK10 impact, which is 20 joules of energy input, is that there.
And so do you do that on the screens as well?
Yeah, so we'll do it on at least 5 locations on the screen.
Yeah.
And at first, early in the product's development, you'll find issues mechanically, and those can easily be mitigated as we have in the case of CP250.
Very good.
Vibration is another case scenario.
Earthquakes.
Yes, earthquakes indeed. In California, you will have seismic zone 2 earthquakes, which is about Richter scale 6, every couple years. And if you want to represent 10 plus years of exposure for a product, you'll have to run 5 plus earthquakes for the product in a given sample that's in test. And we'll actually run the full test with power output, same as we would for water ingress, the way it would happen in the field. But of course, there's package vibration. That's the stress that every unit is going to undergo when it's going out into the field. So we'll have fully packaged production units going on the vibe table, running truck profiles, air profiles to simulate that aggressive transport.
So do you have a drop test as well? I mean, these things do come, out of trucks, and sometimes stevedores aren't the gentlest guys on the planet. So you do see, things that fall down. What do you do? Is it a 6-foot test? That's kind of like common.
That's a great question, and
or
as part of the standard sequence, is actually transport vibration followed by package drop.
Yeah.
So at the larger size packages, it's a rotational edge drop, where you'll have a large crate sitting on one edge, and it's like a heavy set down with a forklift, for example.
Right.
And that'll be dropped 6 inches onto that edge. And then for the smaller packages, where it could go on a UPS truck or handled single-handedly, those will go through larger height, 10 orientations of drop, as is possible in the field.
Yeah. So those ones are at 42 inches, correct?
They can go up to 42 inches.
Yeah,
it depends on the weight. There's a correlation between that.
Yeah, right.
So this is a Z-axis, Richter scale 6, and then we'll have X and Y axes as well. So we talked about solar radiation. UV exposure is the most aggressive for plastics, coatings, and anything that can degrade and cosmetically have issues over time. So we focus on UVA concentrated testing, both in this chamber and 2 other chambers that we have for weathering effects as well. And so not only will we look for cosmetic issues, but we'll look for embrittlement of plastics, for example. So a logical sequence would be doing impact or drop test after you do a long-term UV exposure test. And we'll do this on connectors. Anything that's external facing is going to get that heavy sun exposure. We'll put through UV. And we do go one step further, because customers will be touching surfaces of these products, connectors, the screen. All these have coatings and materials that could degrade with chemical exposure. So your hands have sweat, lotion, oil. So we have a bottle of artificial sweat in the lab we test with. We have sunscreen, lotions that could be aggressive. And then you have cleaning products. Some owners are going to be aggressive about keeping their stations clean, and so we'll have to apply those as well. And then finally, you can imagine stops along the highway being associated with food facilities as well.
Go ahead, you can spit it out.
Sure, right.
Yeah.
And so condiment testing, like ketchup, mustard, vinegar, olive oil, we test for all those.
Yeah. Well, one of the things that I found out when I was a kid, I had acne, serious, like cystic acne, and they wouldn't allow me to touch. So I was a tool maker before I was an engineer, and when we did fine grinding, like surface grinding and polishing, Sandy does not touch anything, because if I touched it, we would instantly have all my fingerprints in rust right on me. Okay. So it's that was the most dramatic test that we used to have for automotive, was that, I don't know what it is, an acid or something that your body creates.
Yes.
And that was serious stuff.
Yeah, long term that can accumulate and cause a lot of degradation. So what we do actually is, after we apply the chemical, we age it either with UV or temperature humidity to speed up that wear process.
Yeah, cool. Excellent.
All right, so if we keep going, we'll talk about the environmental chambers soon, but before we do, let's talk about dust test.
The which test?
Dust test.
Oh, dust. Oh.
So we built this chamber ground up.
Yeah, there we go. That's why we can do the old soft shoe on this one.
Exactly.
Yeah.
So we built this chamber from scratch. Simple concept, but not easy to make functional.
Yeah.
And right now we have the chamber loaded with talcum powder, but for reliability purposes, we actually test with Arizona desert dust.
That's
So we have certified desert dust that we procure, and we create 8-hour desert storms with it in this environment, and really speed up the accumulation of that dust over time. And we'll look at a couple samples, but you can see this is the fine brown specks of dust you see there, and that's quite a large range with all the metal oxides that can be abrasive for contacts, and it can accumulate in airflow pathways that then cause temperature rises that could be unfavorable.
Excellent.
All right. So if we go around the corner here, we have all of our environmental chambers. So we have over 12 chambers at the facility that are capable of going down to minus 70 Celsius up to 155, and we'll run a suite of different environmental accelerated tests, be hot and humid, thermocycling, condensation, freezing condensation. We'll also run a validation test where we'll go to the corner cases and make sure operations and all functions are maintained. And the 3,500 plus samples that we put through the lab every single year will each spend some time in these chambers, depending on what the goal of their test sequence is. And the accelerated environmental tests are really a staple of reliability assessment.
So one of the toughest tests that you could put an ICE vehicle through was the snow choke test. So the product, the car, normally would be faced into basically a blizzard, and you'd choke the whole front end of the vehicle, your radiator and whatnot would be, and your engine compartment would be full of snow. Do you do something like that for these as well, or?
That's a good question. And really in those scenarios, you would be concerned about a couple things. One would be the limited airflow.
The fans are usually your biggest problem.
Yes.
Anywhere there's a fan.
Correct. And so for our case, cases where you're going to have limited airflow are captured in our validation tests, where we'll simulate cases where the fans are off, and we'll try to operate the system and study the behavior and see how the temperature sensors respond, and see if the algorithm needs to be adjusted to capture those case scenarios and protect the hardware and have proper faults and warnings in place. So the key part of that is to understand and characterize it if we know that that's going to happen in the field, and be able to manage it real time.
Yeah.
So in this chamber we have running a humidity freeze test, and if you'd like I can give you a peek inside.
Yeah, it'd be great. So you can see this is a -40 environment with the power block in there, and we would run long-term exposure aside from validation testing at these conditions. Right now it's non-operational, but obviously during actual tests we would run this fully operational, outputting maximum power, and different conditions that are critical for long-term stress. So those would be the fans that failed on brand X.
Yes, correct.
And the reason they failed was because they were choked with snow. So I assume there's louvers or something here in front of this, correct?
Yes, right. There is. There are baffles, and there's a bug screen as well that would block.
That could be blocked.
Yes, correct.
Yeah.
And the other thing to note is when you have a design that's modular,
Yeah.
and follows a field replacement plan like our systems do, it really allows you to quickly swap
Repair,
parts
yeah.
out. So when you saw in there the power block had a set of 6, those are actually grouped in 2s, and each of those are in a fan tray that you can slide out and replace in less than 30, like opening up the system, shutting it down, replacing that and bringing it back up should be possible within 30 minutes.
Well, unfortunately, things were pretty nasty for about 2 weeks, so it may have been easy to replace them, but nobody was replacing anything. Everybody was kind of hunkered down.
I see, okay.
Yeah.
So
Here we have.
with all of the reliability testing we do here, the value really comes through when we can do failure analysis.
Right.
And understand not only what failed, but how did the stress actually cause the degradation to then cause the functional loss, because that's how we can understand, first of all, what to go change to improve.
Right.
And that's how we can help say what that means for the field. So if it happened, let's say over 4 hours in our test, what does that suggest for how long it takes for it to happen in the field? So we have to answer that question so we can better understand and assess risk. So let's say if, for example, 4 hours on our test represents 25 years in the field, well, that's a different risk assessment than if 4 hours on the test represents only 6 months in the field.
Yeah, right.
Yeah. So in that regard, we've built a critical FA lab in-house in our facility here, and our FA engineers will run failure analysis for us as needed. So we have critical tools like X-ray, cross-section, we have scanning electron microscopes, we have EDS capability, and a slew of test setups where we can debug PCBA primarily failures, because PCBAs are such a critical functional part of the system. Yeah. Right. Let's see if we can take a peek inside of our FA lab. So you can see we have our scanning electron microscope with EDS capability, some high mag microscopy, and then a series of scopes and setups where we can really debug and isolate failures to particular components. And we really need to be able to decipher whether the root cause is design-based, manufacturing process, or materials quality, so we know where to go look for corrective actions.
Excellent. Yeah, this looks like a nice little test lab.
Yeah. And of course, there's far more tools you could have for failure analysis, and we have external labs that we go to as needed to speed up that learning process.
Yeah.
After you.
Thank you.
So that just about gives you an overview about 90% of what we do here to cover reliability and really have a accelerated loop of learning for the engineering team in growing that reliability to the point where it's ready for the field and mature enough. And also giving us opportunities to very rapidly learn as new findings come through from the field. And that's really key because the charging industry is so new. So there's going to be use case scenarios, there's going to be long-term stresses that will come with new learnings and new risks, and we'll have to be able to capture that quickly, and this facility will give us that opportunity.
Well, this has been a very, very good tour. Thank you so much.
Thanks for your interest.
I really, very interested actually. So I think this is going to be the conclusion, and so I'll do the wrap up right here. I'd like to thank ChargePoint for allowing us to come in and have a look. As I've said a couple of times already, I am skeptical, or was skeptical. This looks pretty good as far as I'm concerned. I like the business model. The machines look like they can get the job done. I like the fact that they're moving ahead on, everybody's moving toward the Tesla, the North America charging system. I think all in all, this was a good value for my time. So anyways, thanks again to everybody, Michael, for making this all happen. And thanks for watching Munro Live. Thank you.